So, good evening, everyone. We'll start with today's problem solving session. So, for this week, we'll be delving into the state space representation for dynamical systems, and we'll be coming out of the standard classical methods of trying to analyze, model, and control dynamical systems that were primarily based on the transfer function approach, the the transfer function approach, which gave us pretty much some time domain methods to analyze systems and some frequency domain methods. But one big disadvantage of that approach is that it is valid only for linear systems. And whenever nonlinear systems comes into play, we just cannot do any analysis with that approach. Yeah, so with that, we'll begin with today's problems that will essentially deal with state space representations of dynamical systems and some very basic things like equilibrium points and so on. So, for first question, we have find the equilibrium point or maybe multiple points of the system given by these equations. Okay, so at first glance, this looks like a very complicated system, and like it might be very difficult to solve this thing, but let's just try our hand at it. Yeah, so we want to find the equilibrium points of the system. So know that whenever we have some system like this, x dot is equal to some f of x, then what we want to do is to find the equilibrium points, we want to solve for f of x is equal to 0. That is, at these points, there is no velocity to the states, right? Like if the state is at this point, then it wouldn't move anywhere away from it unless perturbed. So with that in mind, we want to find the equilibrium points for this given state space representation. Okay, so basically we need to equate these two things to 0, and let us take the second equation first and this component first, right? Uh, let's take this 4x1 x2 sine x1 minus x1 minus 2. And so basically what I'm trying to do is I am trying to decompose this x2 dot entire expression into two parts. One which is looking a little awful, this sine term, and the other one which is simply polynomial in the things, this term. So let's just try to get this polynomial factored in. So if we do that middle factor, something that we did in class 8 or so, right? In that, I guess if we do it like this, what do we get? This is x1, x2 minus 3 minus 2, x2 minus 3, right? So this is x1 minus 2, x2 minus 3. And if we take this thing, so basically what we want is we want this entire expression to be equal to 0. We want to find all possible x1 and x2s where that is true, right? So for this entire expression to be 0, one possibility is this first term is 0 and the second term is 0. So let us look at that. If we have this, right? So first term is 0 where at x1 equal to 2 and x2 equal to 3. Or like it is 0 at both of these points. Then what do we have here? Here again sine x1 minus 2. Uh, like I'm not taking all the pi multiples and so on. Let's just keep things simple for now. So x1 equal to 2 is one solution for this. And then here x1 equal to 0 or x2 equal to 0. Right. So these three possibilities make this term 0. These two possibilities make the first term 0. So all in all, x1 equal to 2 and x2 equal to 3 make the entire second term 0. Is that not right? No, actually, in this, x2 equal to 3 is not cannot be included. We only have this thing, right? Because when x1 equal to 2, this part is 0 as it is factored this way, and this part is 0 as this sign term is there. Now, on the other hand, okay, so let us wrap this up for the second equation and then move on to the the first equation. So I'll write the entire term in the next page. X1 dot is equal to x1 square x2 plus x1 x2 square minus 3x1 square minus 2x2 square minus plus 6x1 6x2. So we want to find for what values of x does this equation satisfy. So can someone help me? Like, can you see any pattern in how to decompose this equation, or if we can some way get some values? Take some time and try it out for yourself. Let's see if we can get some solutions. So which two parts should we? Okay, let's take. Okay, second order terms are these things. These are third order terms. What about these? Okay, let's try that. Uh, okay, let's say x2. No, I don't understand. Okay, these are the second order terms. These are the first order terms. These are the third order terms. What are you suggesting me to do? Yes, were you saying some way to go about it? Okay, let's try it out for some times. Then we'll see in say 1 minute or 2 minutes. Okay, I'll give one hint. Uh, okay, let's put it this way. Okay, so this entire term is decomposed into these two sums plus. Let's see, right? Yeah, now what can we do? Is there some pattern or something? Okay, so if you look at the first upper line, then we have something like x1, let's take x1 common, x2 minus 3x1, sorry, x1, x2 minus 3x1 minus 3x2 plus 6, right? Then here plus x2 common, x1, x2, ah, just a minute. Okay, maybe I'm making some mistake here. Okay, I can put it this way. Okay, let's erase this. Right. And look at it just a minute. So x1, x2 minus 3x1 minus 2x2 plus 6x1. So what is this part? This is x1 square x2 minus 3x1 square minus, okay. So just a minute. Let's try to decompose this thing into, yeah. Now try to decompose this. Now it should be easier, I guess. I made a mistake earlier. So let's try it for 1 minute. This you should be able to factor it into some easier chunks. Yeah, let's do that. x1, x1, x2 minus 3x1, 2x2 plus 6 plus x2, x1, x2 minus 2x2 minus 3x1 plus 6. Right? So this term that we get, it is common on both these things. So this is basically x1, x2 minus 3x1 minus 2x2 plus 6 into x1 plus x2 equal to 0. Now remember this term, that underlined red term also came in the earlier expression, right? So this is x1 minus 2, x2 minus 3, x1 plus x2 equal to 0, right? So this is also satisfied by these, right? So the first equation is satisfied by these three solution sets, while the second equation is satisfied by only this solution set, right? So we can take that x1 equal to 2 is a valid equilibrium point, but this is not a single equilibrium point. But for x1 equal to 2 and any value of x2, my fx will be 0, right? So if I take x1 equal to 2 in the first equation, I'll have 0. And if I take x1 equal to 2 in the second equation, then also I'll have 0, right? But say, and that is quite independent of what value x2 takes. Whatever x2 may be, this entire thing is decomposed into a factor of this. So x1 equal to 2 means this entire thing is 0. And similarly, this thing is factored into this. And this one has the sin x1 minus 2 term. So for x1 equal to 2 and all possible values of x2, we'll have equilibrium points for this system. So is it clear? I know this first example is a little messy and big, and probably you won't get problems like this in the exam. But this just gives us an idea like what is the aim behind trying to find equilibrium point. Like how do we go about trying to find the equilibrium points? So is it clear? Okay. So now we'll move on to some simpler examples. So consider the nonlinear system given by these two. Find the equilibrium points of the system. Further linearize the system about these equilibrium points and comment about the stability of these equilibrium points. Okay. So we have now, okay, one of you tell me what do we do with trying to find out the equilibrium points. So I equate this to 0, I equate this to 0, and then what do I do? Like this should be fairly straightforward to solve. So can you help me with what are the equilibrium points? X2 is equal to and x1 equal to from these two equations. 0, 0 is one possibility, yes. What are the other ones? Let us just write out what is the solution to this equation. 2x2 minus x2 square is equal to 0. So what are the solutions? X2 equal to 0 as you've told, and the other one is 2. And for this case, yeah, for this case it is x1 equal to 0 and this is 1. Right. So now these are the solutions of this, like these fx equal to 0. But what are the equilibrium points? Like know that equilibrium points are points in the R2 plane for this x1 x2 system. So what are the equilibrium points? Tell me. 0. See, 0, 2 and 0, 1, these things are solutions for this that fx equal to 0. But the equilibrium points are these 1, comma 0. Right. So x1 equal to 0, x2 equal to 0, one possibility. X1 equal to 1, x2 equal to 0, another possibility. X1 equal to 0, x2 is equal to 2, one possibility. And x1 equal to 1, x2 equal to 2, the final possibility. Right. So these four equilibrium points exist for the given nonlinear system. Is it clear till now? Yeah. So now what we want to do is linearize the system about these points and comment on their stability. So for linearizing the system, x1 dot is equal to x2 minus x2 square and x2 dot equal to x1 minus x1 square. So we want to find out the Jacobian, right? So J is equal to, this is F1, this is F2. So we'll have dou F1 by dou x1, dou F1 by dou x2, dou F2 by dou x1, dou F2 by dou x. So this is dou F1 by dou x1 is 0, dou F1 by dou x2 is 2 minus 2x2, right? And dou F2 by dou x1 is 1 minus 2x1 and dou F2 by dou x2 is 0. So, yeah, this is the Jacobian. So let us, or the A matrix, because the linearized system is this about some operating point, and we want to find it about the equilibrium points as the operating points. So let's first find out for 0, comma 0. There, A is given by, we'll plug in 0, 0 into the Jacobian. So 0, 2, 1, 0. Right. So what are the eigen? Is it clear till now? Okay. I was, yeah. Okay. Thanks. So then we want to find out the eigenvalues to make some comment about the stability. So let's do that. So eigenvalues are given by, we want to equate that equal to 0. So this is, let's find that matrix, right? And its determinant is lambda square minus 2 equal to 0. So this implies lambda equal to plus minus root 2. Is it correct? So here the eigenvalues are plus minus root 2. So from this, what can we tell about the stability of the system at the equilibrium point 0, comma 0? Is it a stable equilibrium point, an unstable equilibrium point, or can we say nothing? What do we say? Okay, so on this, that if there is a single, yeah, if there is a single eigenvalue with real part greater than 0, then the equilibrium point is unstable. Alright. And on the other hand, only if all eigenvalues have negative real part, then it is stable. And if real part equal to 0, then we can't say, right? So, and all of this is only local behavior. Local behavior in the sense that, say 0 comma 0 is an equilibrium point, right? So the system around this, the trajectories will be unstable. That is, they'll be going away from this equilibrium point, right? So something to that effect. So is it clear till now? Okay. Then we move on to the next other equilibrium points. So A was 0, 2 minus 2 x2, 1 minus 2 x1, 0. Right. So at what were the equilibrium points? 1, comma 0. At 1, comma 0, A is 0, 2, minus 1, 0. Right. Now here the equation for eigenvalue, uh, this one, yeah. So lambda square, here we'll have lambda square plus 2 equal to 0. So that will give me lambda equal to plus minus j root 2. Now here see that all the lambdas have real value 0. So here we cannot say anything about the stability of the system. This is a like a flaw of linearization. We just can't say anything about it. Okay. Then for the other system 0 comma 2, A is, we'll put in 0 comma 2, so this is 0 minus 2. So again here also we'll have lambda square plus 2 equal to 0, that is lambda is equal to plus minus j root 2. Alright, and for 1 comma 2 we'll have a equal to 0, minus 1, minus 2, 0. That will give me lambda square minus 2 equal to 0 and lambda equal to plus minus 2. So for these two equilibrium points, since there are no, like the real value of all the eigenvalues is 0, we cannot say anything about the stability of the system around that equilibrium point. But on the other hand, for this equilibrium point and for this one, we can say that it is unstable near that equilibrium point. So that is all we can comment about the stability of the system from linearization. For further techniques, we'll have to delve into nonlinear analysis, which is beyond the scope of this lecture. So, is it clear till now? We just linearize the system about an equilibrium point, see the eigenvalues, yeah, and then get some idea. So now this is a very simple problem. Like this is just a one-dimensional system. X dot equal to x minus x cube. So this is x 1 minus x 1 plus x. Right. So comment on the stability of the equilibrium points. So why I chose this question is now we can see in a sense. Let's take 0, 1, minus 1. Right. So in these different sections separated of the real line separated by these points minus 1 0 1, we can find the signs of x dot, right? X dot is I guess greater than 0 here. No, it's less than 0 here. Just verify once. At 2 we have 2 1 minus 2, yeah. So this is here it is greater than 0, here it is less than 0, and here it is greater than 0. So what that means, suppose I start at a point on the line here, then at this point x dot is greater than 0, right? So if I start at say x is equal to 0.5 and I have x dot is greater than 0, then what do I get? Like x dot x, say I start at x not equal to zero point 0.5 and x dot is greater than 0. So x of t will increase from zero point 0.5, right? Since the derivative is positive, so the value will increase. So say I start at this point, my value will increase. Again there also x dot is positive. Again it will keep increasing. It will keep increasing till it hits this point. Alright. So at this point it reaches an equilibrium point. So it should stay there, right? Because obviously here x dot equal to 0. So from here, unless someone else moves it, it won't go as per these dynamics, right? So then take this area. Here x is something greater than 1 and there x dot is less than 0. So it will decrease, it will keep decreasing till this point because here x dot equal to 0, so there won't be any change anymore. So if I start from somewhere here, I'll come here. If I start from somewhere here, I'll come here. Right. And look at this part. Let's just mark these things. Then in this part, x dot is less than 0. Right. So again, x will decrease here. So it will go to this equilibrium point away from this 0. So again, here it is this way. And at this point, x dot is positive. So the value will increase. It will go rightwards. So it will come to this point. So again, this is this one. Now let us linearize the system. X dot, I don't know if this will work out, but if I linearize, then like this is basically f of x is x minus x cube and dou f by dou x only because this is a single dimension thing. So this is 1 minus 3x square and we'll have three equilibrium points minus 1, 0, 1. Right, so at minus 1 and 1, we'll have this is minus 2 and at 0 we'll have this is 1. So x dot is equal to minus 2, x dot is equal to 1 and x dot equal to minus 2. These are the three, like around the equilibrium points, these are the three linearized systems, that kind of thing. So this system works around this system works around this system works around this, right? So, mm, yeah. So, okay, sorry. This will be the thing because x dot equal to f of x. Linearized is x dot is ax, where a is the Jacobian, and this, so basically here the Jacobian is just coefficients. So clearly these are stable ones, right? And this is the unstable one. Okay. So this is what we mean by stable and unstable equilibrium points. So if you look at 0, it is an unstable equilibrium point as given by this. Why? Because at that equilibrium point, you won't move. Because if you are at 0, x dot is 0, there won't be any change. But say you are nearby here, or there is some perturbation, then you will never come back to 0. You'll keep going away from it in either direction. And for 1 and minus 1, it is the opposite. If you are perturbed from 1, you'll again be brought back to 1. You won't be able to move away from it. So this is like, say you are on a, there is something like this. This is, say, a hill kind of thing, hill and valley and hill. If you are at the topmost point of the hill, say it is parallel slope, then you'll stay there. Like, not you, like a ball, let's say. The ball will stay there unless there is any disturbance. But once there is any disturbance, it will never return to the top of the hill. It will go away from it. But on the other hand, if the ball is here, then no matter whatever disturbance is that, I mean, not whatever, but if the disturbance is within some acceptable region, it's say brought to here or here, then it will roll back down. So that is the physical significance of these stable and unstable equilibrium points. Okay, so I think I spent quite a lot of time on these equilibrium points. Let's move ahead. Yeah. So, given the state space representation of a system, find the transfer function. So we know this is the standard thing. So we want to find the transfer function. So for transfer function, we'll assume all initial values are 0 and those things. So this will give me AXS plus BUS. That means from the first equation, right? So this means XS is equal to SI minus A inverse B Q of S. And from the second equation, we have I of S is equal to C X of S plus D U of S. So plugging this here, we have C Si minus A inverse B plus D whole into U of S. So that means we can take this the other side. So for any general state space representation, this is the transfer function, right? So for this, since D is 0, we want to find out C Si minus A inverse B. Okay. So is it clear till now? Yeah. So okay. So C is this 1 0 0. We have some matrix and then this is 0 1 1. Right. So A is 1 1 2 0 1 3. So Si minus A is S minus 1 minus 1 minus 2 0 S minus 1. Yeah. And then Si minus A inverse is the return 1 by delta, the determinant, and adjoint. Right. So let's first find out the determinant. It is S minus 1 whole into S square minus S minus 6 plus 1 into minus 3 minus 2 S minus 1. So this gives me, let me just check. Yeah, S minus 1 F minus. Yeah, so is it correct or no? You can also verify it. Then this gives me S cube minus 2S square minus 7S plus 5. This is the determinant. Now note that we need not find the entire SI minus A inverse matrix, right? So here we have 9 elements. So when I multiply this with this matrix, what do I get? So this row is multiplied with the columns, right? So only the first row of the matrix remains, right? Because say this is multiplied with this, then these two elements are multiplied with 0. Similarly, these two are multiplied with 0. Similarly, these two are multiplied with 0. So in the end, 1 cross 3 into 3 cross 3 will give me a 1 cross 3 row vector, and that will be just equal to this. Then further, this matrix, so let us write it that way. This is equal to just some row vector, which is this one, same thing, and then it is multiplied with 0, 1, 1. So here again it is only multiplied with these two, and those two things are added. So let's take this is A1, A2, A3. Then we'll have A1, A2, A3 here, and this is A2 plus A3. So now what does that mean? So we just need to find out A2 and A3. That is the adjoint matrix, those two terms. So the adjoint of Si minus A, right? So it is that transpose of that cofactor things. So if you have C11, C12, C13, C21, C31 and so on, then it is this transpose. So for finding these two elements, we need to find these two elements, right? So this cofactor for this matrix will be given by this determinant multiplied by minus 1. So see that A2 thing is minus of minus 1 s minus 2 minus 2. So what is this? Minus of minus s plus 4. Is that right? No, minus 4. So this is s plus 4. And then A3 is similarly the this determinant. No minus sign now. So that is 3 plus 2s minus 2. That is 2s plus 1. So then A2 plus A3 is 3s plus 5 and the determinant whatever. So the transfer function is y by u is 3s plus 5 by the determinant s cube minus 2s square minus 7s plus 5. So is it clear? Okay. So then we consider yeah, a given transfer function of this form, a third order system. Then we just want to write the state space representations in the controllable and observable canonical form. So this is just very simple. So I'll just give the general version. Let's say this is this, right? Then we have the CCF form is 0, 1, 0, 0, 0, 1. Then for the last one, we'll have minus A3, minus A2, minus A1, and B is 0, 0, 1. C is B2, B1, B0, and D is 0. So for this Example, B is fixed, no issues there. For this, it is A1 is 3, so minus 3, A2 is 2, yeah, so this is the thing, and this is B2, B1, B1, 6, 5, right? So this is straightforward. You know the representation of controllable canonical form given a transfer function. You just plug in the values, and there we go. And for the observable canonical form, again we have a very similar thing. Minus A2, A1, minus A2, A3, 1, 0, 0, 0, 1, 0. B is equal to B0, B1, B2. C is equal to 1, 0, 0. Now, see here that this is very similar to this one. In fact, the A matrix there is the transpose of this. The B matrix there, like the C and B are kind of exchanged. And so, yeah, you can see, right? And so this is minus, and this is what is B2? Yeah. So there we go. So this way you can give an transfer function, you can quickly write them in the controllable and observable canonical forms. Now, okay, yeah. Then we want to find out, given a matrix A, I want to find out the matrix exponential of it. Right. So how do we do that? We know that e to the power A is equal to I plus A square by 2 plus A cubed by 3 factorial and so on. Right, the whole infinite series. But clearly, given matrices, and if it does not cancel out or do something like some pattern emerges very soon, it gets really difficult to solve a series like that. Like we just can't do it. So we want to find alternate methods. So what we do is we want to diagonalize the uh, matrix A. So how we do that is we first find out the eigenvalues, right? So for eigenvalues, we want to find out determinant of this and equal to 0. So we have determinant of lambda plus 2 minus 1, 3, lambda plus 1 is equal to 0. This implies lambda square plus 3 lambda plus 2 plus 3 is equal to 0. So yeah, what is the determinant here? Let's find out. Let's put it in the calculator. Okay, so here we get plus minus two conjugate poles. Just a minute. Yeah, so this is just minus 1.5 plus j plus minus j 1.658. Yeah, so this one we found out two eigenvalues. Then corresponding to these eigenvalues, we'll find the eigenvectors, right? That is, we want to find all the x that satisfy these. So again, lambda I minus a x equal to 0. So basically, we want to find out all the vectors in the null space of this lambda I minus a matrix. So when we do that, so let's try this example in MATLAB, because as you can see, doing things on pen and paper becomes really difficult very soon. But obviously, like if you have some easier eigenvalues, like not complex or things like that, then sometimes you'll get some easy calculations. But in general, in real life, usually having a like programming software or something is definitely more helpful. So I'll switch over. Yeah. So is my screen visible? Okay. So let's first put in the A matrix. Okay. So we have minus 2, 1, minus 3, minus 1. So this is the A matrix. Then we want to find out the eigenvalues and the eigenvectors. So we have a very convenient thing here. So that gives me, right. So this single command, what it does is it gives me two matrices, one V matrix, the other D matrix. So the D matrix is the eigenvalues, the diagonal elements of the D matrix. It is a diagonal matrix, and those elements are only the eigenvalues of the given input matrix, that is A. And V is consists of columns which correspond to eigenvectors of the given eigenvalues, right? So from here we can obtain the eigenvectors. So I'll stop sharing this again. I'll start sharing this. Yeah, so from MATLAB I'll just copy down these values, and the V matrices. Right, some complex values, no need to worry about the actual numeric values, but yeah. So this V matrix, then what we want to do is we want to find that diagonalized thing, which will obviously be the only the eigenvalue terms. But how that is obtained is D is equal to V inverse A V. Then it turns out that good for us, e to the power at. So from here you see that A is equal to V D V inverse, and e to the power at, if you plug in that A value into this, let's just say e to the power A is, okay, let's do that. I, just a minute. Okay, e to the power A is equal to I plus A square by 2 and so on. So I can write that as V inverse. We'll just pull these out. Right. So this is I. Then A is this thing, V dV inverse. So this is D. Then A square is V dV inverse V dV inverse. So this is V D square V inverse. So this can be written as D square by 2 and so on. We can do this for the entire series. So it's just V e to the power D V inverse. So that gives us a very convenient way. Where is that? Yeah. So yeah. So this gives us a very convenient way to compute the exponentials of any general A matrix. Just a minute, I think. Yeah. So now we have, yeah, so, and why we want to do it this way is that since D is a diagonal matrix, some A here, B here, 0 here, 0 here, so e to the power D turns out to be very simple. It is just e to the power A0, e to the power B. So then this can just be found out by some matrix multiplications. So that's it. So that is why we go through this method, and yeah, the rest numerical values you can calculate, or let us do that. So before we do that, let us just take a look at the next problem. This one will be a long one, so let's not do the full solution here. But to basically find the solution to a matrix differential equation. So if we have something like this, we know x of t is it were 80 x naught, and yeah, x naught. But what happens when it is some matrix? Then also turns out, thankfully for us, this is it were 80 x naught. But things become a little more difficult. We have some integrals and stuff when the u control term comes in. So if for any general system the solution is given by if I remember, yeah, p phi tau v u tau d tau. Yeah. So now this is just a scary looking expression, and the computations become really lengthy, but there is no conceptual difficulty in this thing. Like if you are given A and a B matrix, then all you need to do is find the matrix exponential corresponding to A, plug in these values, U will be given. Let's say U of tau is the standard unit step. Then this is just 1, right? And then we just compute the thing. We find out e to the power. Okay, let's do it for this one. E to the power at. Let's see if it will be simple, or if it is complicated, we'll leave it. First, we'll try to diagonalize. I'll use MATLAB for this so that we can have a faster. Yeah, so you can see my screen, and A is equal to 0, 1, minus 2, minus 1, and I'll write P comma D as again I. Excuse me. So yeah, e to the power at will just be e to the power dt, like v into e to the power dt into v inverse. So let's do that. So I'm taking a symbolic variable t and finding. Let's see if this thing works out. Yeah, it works out. And yeah, so we have this value for e to the power dt. Now we just need to find out v into that exponential of d into inverse of v, right? So yeah. So there we'll have some lengthy expression and whatnot. Okay, this is okay. So if you solve it via calculator, you won't get these long things. These are some computational issues. Yeah, but what did we want to find out? Just a minute. Yeah. So then this will give me the exact solution. Then I'll just plug it into that integral equation For a matrix, integration is just element-wise integration, and just the thing is, it is just a lengthy process, but procedure is this only. No matter how many dimensions you have or whatever you have, this is the procedure that you'll have to follow to find out the entire solution. And yes, it is very difficult, much more difficult than, let's stop sharing, than solving for a standard scalar equation. But the kind of generalized procedure is pretty much same for all sorts of these problems. So is it clear what we did today? Or was it a little too rushed? I feel I rushed it a little bit. But I hope the concepts are clear. Yeah, okay. So any doubts for today? Or can we wrap it up? Okay. Thank you for attending this session.